In the last lecture, we talked about a powerful principle which is called the principle of locality. And this principle of locality naturally leads to the idea of fields. In general, the field is represented by phi a of x comma t. Here a is a label. At this stage, classical field theory is classical mechanics with infinite degrees of freedom. Action has a local form, that is single integral of the Lagrangian density. Which is a function of phi a and derivative of phi a. Now the momentum density that is conjugate to each point in space is given by pi a x comma t, derivative of the Lagrangian density with respect to phi dot a x comma t, and the Hamiltonian density corresponding to this action is pi a phi a dot minus Lagrangian density. Now varying the action, general form of the equation of motion can be obtained, and the general form of the equation of motion is given by now for a single scalar field phi of x. Okay, so if you consider a real valued single scalar field phi of x, then the action can be written as okay, and the corresponding momentum density will be phi dot, and the equation of motion is given by so this is just the recap of what we have seen in the last lecture. Okay, in this lecture we start with the symmetries and conservation laws. So in the context of field theory, what is symmetry? So symmetry is some transformation of each field phi a into some other function phi a prime. Okay, so what do you mean by symmetry? So some transformation of your dynamical variable which leaves the action invariant. Okay, if you see, the form of the dynamical variable have changed. Now it is phi prime. Okay, but still it's just the labeling changes, the value will not change. Okay, so symmetry is some transformation of each field phi a into some other function of phi a prime. Okay, so the transformation of the dynamical variable should leave the action invariant. So symmetry, some transformation of the dynamical variable that leaves the action invariant. Okay, first we will discuss translational symmetry. Okay, if you have a coordinate x mu You transform it to x prime mu by adding a constant. Okay, here a mu are constants. Then the field phi of x will be transformed to phi prime of x prime. Okay, so here you can notice that the labeling changes but value does not change. So the new field phi prime evaluated at the new location should be the same as the value of phi at the original location. Okay, so if you see the action, then if phi is invariant, and then again the action is also invariant. So the scalar field will transform under a general space-time coordinate transformation as phi of x is equal to phi prime of x prime, which means that the labeling changes but value does not change. And the second type of symmetry that we'll be seeing is the Lorentz symmetry. So in Lorentz symmetry, again you transform the coordinate x mu to x prime mu by giving a Lorentz boost or a rotation, which is represented by this matrix, right? So this matrix is the constant Lorentz transformation matrix. Okay, and again phi of x is equal to phi prime of x prime, right? So this translation and Lorentz symmetry are also known as continuous symmetries. Okay, so translational and Lorentz symmetries are called as continuous symmetries. So continuous symmetries are transformation, okay, which involves continuous parameter, okay, something like this. So here a mu is a 4 vector. You can see that in the first case, a mu is a 4 vector, which involves 4 members, and it can be arbitrarily changed continuously. And in the second case, you have the Lorentz transformation, you have the Lorentz metric, which has 3 rotations, which can have 3 rotations and 3 boosts, which means there are 6 continuous parameters. But if you see the action here, it has other symmetries that are not continuous. Okay, for example, if you see here, then if you transform phi to minus phi, then again the equation is invariant. Similarly, parity, if you put x as minus x, if you transform x to minus x, then again the action is invariant. Because, okay, so in both these cases the action is invariant as it is quadratic in phi. So they do not involve continuous parameters. Therefore, such symmetries are called discrete symmetries. Okay, do not involve continuous parameters. Now both of them are also called as the set 2 transformations, which means if you do the transformation twice, So if you do this transformation twice, then it will go back to identity. So such transformations are also known as Z2 transformations. Okay. Now symmetries can be classified into continuous or discrete depending upon whether you have continuous parameters or not. So that is the gist of this section. Okay. Another classification is based on the space-time dependence. If corresponding transformation parameters are space-time independent, then they are called as global symmetry. And if the transformation parameters are space-time dependent, then they are local symmetry. Okay. So example for global symmetry will be the translation symmetry, right, and the Lorentz symmetry. And example for the local symmetry will be the gauge transformations in electromagnetic theory, right, that are dependent on parameters are space dependent. Gauge transformation in electromagnetic theory. Now there is a connection between the symmetry and conservation laws. Any conservation law can be understood as a consequence of symmetry. For example, the time translation leads to energy conservation. Spatial translation leads to momentum conservation. And if it is a rotational symmetry, then it leads to angular momentum conservation, right? So in general, there is a connection between the symmetry and the conservation laws, and it's given by the Noether's theorem. Okay, so next we will have a tutorial, state and prove Noether's theorem. Okay, so this is a generalization in the field theory which is given by the Noether's theorem. Noether's theorem states that for every continuous global symmetry, in a physical system, leads to a conservation law. Every continuous global symmetry in a physical system leads to a conservation law. So now we have to prove Noether's theorem. Okay. For this, we start with the continuous symmetry. For any continuous symmetry, it will be having an infinitesimal form. Okay, if it is a continuous symmetry, then it will have an infinitesimal form, which means, for example, if you look at translation, then A mu must be close to 0. And if you see the Lorentz symmetry, then the matrix lambda mu nu must be close to identity, right? For the transformation to be infinitesimal, okay? Because here you have to multiply x prime mu is equal to lambda mu nu times x nu, okay? So for infinitesimal transformation, lambda mu nu must be close to 1. And here you have x prime mu equal to a mu plus x nu. So for infinitesimal transformation, a mu must be close to 0. Okay. So that transformation will be close to nil. Infinitesimal transformation in the sense transformation will be close to nil. Okay. Then the field phi will transform as phi a prime equal to phi a plus some infinitesimal transformation parameter multiplied by some arbitrary function of the fields. Okay, something like this. Then the infinitesimal symmetry transformation will be so here we assume that somehow the theory has a symmetry, and then we want to see what is the constraint put on the theory. Therefore we start in this way. Okay, so by definition you have to vary the action and extremize the action. Okay, so the variation in the action must be 0. So variation of the action must be invariant under the symmetry. Okay, so this must be invariant under the symmetry. Now the variation in the Lagrangian must be of the form epsilon and the derivative of k mu for some k mu which can be 0. Here k mu can be 0. Okay, so it's just an arbitrary parameter. Fine. Now the variation in the Lagrangian density will be of this form. Okay, now from the equation of motion, okay, so here we have the equation of motion. Okay, from the equation of motion I can equate these two terms, because this first term subtracted by the second term is giving me 0, which means I can equate the first term and the second term. Okay, so I'll write equal to and I can substitute it here, right? Therefore I'll get the variation in the Lagrangian density as multiplied by plus the second term as it is. If you carefully see, this is the total derivative, right? Total derivative of this term multiplied by, right? So this is the total derivative. So after using the equation of motion, the variation in the Lagrangian density has a total derivative form. But we have assumed that it will take this form. So I can equate the right hand side of the variation of the Lagrangian density in both the cases. Therefore I can write Now here epsilon is independent of space-time because we are seeing the global symmetry. Okay, so I can write delta phi a in terms of epsilon we have already defined it as epsilon fa. So here epsilon is independent of space-time, therefore I can cancel, take it out of the derivative and cancel, right? So now I have is equal to now I can rewrite this equation as minus k mu is equal to 0. So now this looks like a very familiar form of the equation. If I write this as j mu, then I can write yes. So this you might have seen in electromagnetic theory. We call it the continuity equation. So this is the continuity equation. Okay, so I can just expand and write as the time part and the spatial part. So the time variation of density is equal to the divergence of the current. So we can define a charge q such that, right? Now if I vary both sides, then I'll get, with respect to time, then I can write minus divergence of the current, right, from here, from the continuity equation. Now we can see that at infinity the current will vanish, and therefore this quantity is equal to 0, and this is the field theory version of the conservation of charge. Okay, so this is the field theory version of charge conservation. So whenever we see a symmetry, it is enough to understand that symmetry near the infinitesimal transformation or near the identity, because any finite transformation can be built from just adding up the infinitesimal transformation. So if you know the symmetry near the infinitesimal transformation, that is more than enough. Whenever we see a symmetry, it is enough to understand that symmetry near the identity, or near the infinitesimal transformation. Because any finite transformation can be built from just adding up the infinitesimal transformation. Okay, so this is important to understand that symmetry near the infinitesimal transformation. So that's why here we have taken a small infinitesimal variation epsilon, right? Yes. Now we have seen about classical fields And the next goal is to understand the quantum version of this story. Classical field theory is classical mechanics with infinite number of degrees of freedom. And now we want to quantize this infinite number of degrees of freedom, which will lead to quantum field theory or the quantum dynamics of the field phi. So what is the goal of the quantum field theory? So we have electric field and magnetic field, right? We have electric field and magnetic field. You have Maxwell equation, and this defines the classical field theory. So in this course we will see how to quantize such a system to understand the electric and magnetic field quantum mechanically. Okay, and in the following steps we'll start with simplest field theory, that is the scalar field theory. Then we will go to the Dirac theory. Okay, scalar field theory. Then we'll go to Dirac theory. So Dirac theory will explain the electrons and the spins and stuff. Then eventually we'll go to the theory that describes the electromagnetic fields, which is known as the quantum electrodynamics. Okay, that will be the end of this course. So before going from classical field theory to quantum field theory, let's recall how to go from classical mechanics to quantum mechanics. Okay, so first we'll see how to go from classical mechanics to quantum mechanics. Then next we will see classical field theory to quantum field theory. So in classical mechanics, if you have a single degree of freedom, that is just a one-dimensional particle whose motion is described by x of t, then the goal of the classical mechanics is to solve the equation of motion for x of t. When you go to quantum mechanics, x of t will become an operator, right? And the equation of motion will be now the Heisenberg equation of motion for x of t, right? X will go to operator and equation of motion will be now the Heisenberg equation of motion. There are two ways of describing in quantum mechanics. So one is the Schrodinger picture and the other one is the Heisenberg picture. So in Schrodinger picture, you have the wave function, right, which is dependent on time and time independent operators. And here x is the eigenvalue of the operator x cap. In Heisenberg picture, the dynamical quantity is operator, that is operator are dependent on time, and state do not evolve in time. Okay, so we adopt a similar method in classical field theory. We have the phi, which is function of x comma t. Okay, now if you promote it to quantum, then the field phi will become an operator. Okay, so classical equation of motion of phi will be now an Heisenberg equation for phi cap. Now, out of Schrodinger picture and Heisenberg picture, for quantum field theory, Heisenberg picture is more convenient. Why? So we'll just see. In Schrodinger picture, okay, the wave function psi will be phi of x comma t. But here phi of x are the eigenvalues of the operator phi cap of x. Okay, do not evolve with time. Okay, there is no time, it's only dependent on phi of x. Since phi itself is a function of x, psi will be a functional. Okay, so here phi is a function of x, which means psi is a functional. But in Heisenberg picture, the operator phi evolves with time and the state does not evolve with time. So in Heisenberg picture for field, you can see that the field is now promoted to an operator which evolves with time, and the state of the system psi does not evolve with time. And in Heisenberg picture, you just focus on the operator equations, and once you solve the operator equations, you can calculate the expectation values in any state you want. So if you do with Schrodinger picture, then you have to deal with the wave functional of all possible values of some function in space. If you have multiple fields, then the functional will become highly complicated. In Heisenberg picture, we just solve the analog of classical equation of motion, which we have written down. And you just now interpret it as a quantum operator equation, which is much more simpler. Okay, therefore we use Heisenberg picture for quantum field theory. Now before going to quantum field theory, let's discuss about relativistic quantum mechanics. Okay, so what all you know till now about relativistic quantum mechanics? So till now what we have seen is non-relativistic quantum mechanics, and if I want to incorporate or combine special theory of relativity with quantum mechanics, how do I incorporate special theory of relativity with quantum mechanics? Okay, if this is successful, then we will get quantum field theory. So without quantum field theory, it is impossible to unify special theory of relativity and quantum mechanics. Okay, so let's try to generalize or derive the relativistic quantum mechanics. In non-relativistic quantum mechanics, we know that the energy E is equal to P square by 2m. Okay, so in operator form, E will be I and P will be minus I del. Okay, if I substitute back to the energy, then I will get is equal to minus 1 by 2m, then del square, because here there is a P square psi x comma t. So we obtain the Schrodinger equation. This is for non-relativistic quantum mechanics. Now if you see the relativistic quantum mechanics, then energy E square is equal to P square C square plus m square C to the power 4. So we follow natural units, therefore I can write P square plus m square. Okay, because C equal to 1. Now here if I substitute the operators, then I'll get is equal to minus del square psi plus m square psi, right? Otherwise I can combine it and write as del mu psi x comma t minus m square psi x comma t is equal to 0. So this is nothing but the Klein-Gordon equation. So this is the equation for a simple scalar field, right? It's similar to an equation for simple scalar field, but here psi is not a field. It is a wave function that represents a single particle and its square gives probability. So there are various problems in this wave equation treatment. So what are those difficulties in interpreting the Klein-Gordon equation as a wave equation for a relativistic particle? In non-relativistic quantum mechanics, psi square will give the probability. In relativistic quantum mechanics, there is no quantity that can be used as the probability density. That is, probability density must be non-negative and conserved. Okay. So psi square will give the probability in non-relativistic quantum mechanics, but in relativistic quantum mechanics, there is no quantity that can be used as the probability density. And also the second difficulty is that the energy E square is equal to P square plus M square. So energy is plus or minus root of P square plus M square. So the relativity introduces negative energy, right? So if you can have both positive and negative energy, then in the dispersion relation, you can see there will be both positive and negative energy states that are available, right? And there is a non-zero probability for a particle to go from the high energy to the low energy. So this can be infinitely negative and can lead to instability. So even if you can address these problems, again there is one more fundamental issue in relativistic quantum mechanics, okay, that will not make any sense. The reason is that psi x comma t describe amplitude of a single particle at some point x at time t. If there are two particles, then you have to write psi x1 x2 t. Now this is true for non-relativistic system where particles are conserved. In a relativistic system, particles can be annihilated and created. So this is what happens in the accelerator all the time. Particles are not conserved. Okay. So in relativistic system, particles can be created and annihilated. Okay, particles are not conserved. Therefore, this kind of wave function concept don't even make sense. The annihilation and creation effect cannot be achieved by the wave function, but it can be achieved by quantizing the field theory. So quantum field theory automatically gives a framework, okay, to describe the arbitrary number of particles. And quantum field theory plays an important role in particle physics. The excitation of fields will provide a mechanism to describe the arbitrary number of particles. Therefore, we need quantum field theory. Quantum field theory automatically gives a framework for describing arbitrary number of particles. Okay, so for today we will stop here, and in the next class we will see how this is achieved.